In this video, we want to look a little bit more in detail at one part of what was in the last video. And this is the part talking about local linearity. So I want to look at this part. I'll repeat a few things from the last video and then elaborate a little bit more. So notice in the following graph we see a function, which is this blue function f of x. And so here's a point of interest, let's say a comma f of a. And then we move to the right some distance h, and here's a nearby point, a plus h comma f of a plus h. Now, we know that if h is 1, that is delta x is 1, then the slope of, say, this tangent line is just vertical change over horizontal change. It's delta y over delta x, but delta y is just the change in the f prime, okay, which is over, so this vertical change over 1 is the slope of that pink line, which is the derivative. So this vertical distance right here is the derivative. It's the slope of this pink tangent line. Now, the actual change in the function in this case is the change from this point, well, the vertical change, the change in the function value, delta f, is the change in the y value here at this blue point to the y value at the green. Or in other words, it's the y value from down here in the corner up to here. So this distance, which I've got indicated by this green bracket, is the change in the function, okay, which is actually the slope of the secant line because delta x is 1. So take that delta f over delta x, which delta x is 1, you get delta f. And so this delta f, or this vertical distance from here to here, is the slope of the secant line from the blue point to here, which is the actual amount the function changes when I increase x by 1. Okay? Now, and this distance here, indicated by this black bracket, is the actual change in the tangent line, which is the value of the derivative. Now, what we want to do is we want to say that these two values are not the same, as you can see here. I've made it very dramatic in the fact of what I've picked here, but in many cases these things are relatively close to each other. And so we want to use the fact that the delta f and the f prime are relatively close to each other, and so these two things are sometimes used to approximate each other. But notice that they're not the same thing. So notice in general that the limit as h approaches 0 of f of x plus h minus f of x over h, that is the definition of f prime at a particular x value. Now, so this is basically a limit of a delta f over delta x as the delta x goes to 0. It's another way to write it. So this limit is going to be close. This limit is exactly the derivative. And the difference quotient without the limit, just the delta f over delta x, is close to the f prime of x if delta x is close to 0. And of course, delta f over delta x is delta f if delta x is 1. So what we're saying is the derivative is approximately the same as the change in the function. So we're saying that this black distance here from these 2 points, which is the amount that the tangent line goes up, is approximately the same as the amount that the function goes up, which is this distance here. Not the same thing as you can see in the picture, but they're close. Okay, and this is the part down here that I did not have in the last video. So let's look at this a little bit further. Now, what happens if the function is actually linear? Well, if the function were actually linear, then when you looked at this picture up here, the function would just be following the same line as the tangent line, and there would be absolutely no difference in these two things. F prime of a and delta f would be exactly the same thing when delta x is 1. So what happens if f is not linear? Well, there are a couple of possibilities. Okay, one of the possibilities is that f is well, there are four cases here basically. And so I think I have these kind of summarized in this table. Let me zoom out just a little bit so you can see. all this at once. Maybe I can do it. There we go. So you kind of see all four possibilities here at once, and we'll zoom in for more detail in a minute. So here we've got f is decreasing, or f is increasing. We got f is concave down, or f is concave up. Okay, and so if you're on a small enough piece, and it's it's the derivative exists everywhere, you can probably break it down into a small enough piece to where one of these four shapes is happening if it's not linear. So let's take a look at what's at this. Basically, at this picture that I have right here, at what happens when I look at some various cases. So that one was increasing concave up, the case we've already looked at, and that's the one down here in this corner. So let me see if I can get this to zoom back in. Let's zoom in a bit and see if I can get to my. There we go, and maybe I'll zoom in a little bit more. We can see this. Okay, almost there. Okay, so here we go. So if delta x is 1 and the function is concave up increasing. So here's our graph here. It's the blue graph, dark blue here, and the tangent line is the pink line. So this red distance here is f prime of a, which is some positive number. So we're going the right one. It's going up. The I guess it's a black. This thin line that's a black, which goes from all the way down here at the bottom, traces over all the red and goes all the way up to here. That distance is delta y. So what we see is that f prime of a, okay, is actually a little bit what? It's actually a little bit smaller than the actual function. So the change in y, or the change in f, okay, is actually a little bigger than the change here. So it's actually, the original function, see, is growing more than the tangent line. So it's a slightly above. Again, I want to emphasize slightly here, okay, and not because we want to use these things to approximate each other. So we're going to say that these are close to each other, but slightly different. Okay, now let's look at some of the other cases. Oh, by the way, look at the whole thing. Of course, when you're looking here close by, the tangent line agrees at the point of tangency for the with the curve, but otherwise nearby, notice that the graph of the curve is above the graph of the tangent line, and this happens when the function's concave up. So here's a decreasing one that's also concave up. Look what happens. So it's still true again that the function here is above the tangent line. Of course, it's on the tangent line right at the point of tangency, but nearby the function is a little bit above. Notice that when you're very close to the point of tangency, they look very similar. In fact, if you zoom in close, you'll get they're very hard to tell apart, and so that's what we mean by this local linearity concept. So at the point of tangency, they're identical. As you're close by, they're close to each other, and as you get further away, they get further and further apart from each other, typically. So let's take a look at this. So here we have f of a, f prime of a, and we're going to look and see what happens here. So here, again, we're taking a delta x equals 1. Then we see how far this drop is down to the tangent line. That is f prime. So this red distance from here to here is the derivative, which is a negative amount. It's going down. So a negative slope. The delta f, the change in the function, or delta y, is the drop to get to the graph of the original function. So it's just the, I don't know if you can see it on this video, but there's a black line inside this red one that goes from here to here. And that's the change in the y, that's delta y or delta f. So notice that the graph of the tangent line is actually dropping more than the graph, than the actual graph of the function. So This tells us that delta y is actually greater than delta f. Okay, delta y is delta f. It's greater than f prime. It's bigger in. What about the absolute value? In absolute value, the tangent line is changing more. But remember how we order negatives. This is the red derivative is a larger absolute value negative number, which makes it less than the change in the y, which is from here to here, from this point up to this green line. Okay. Now, on the other hand, if you have so again, when it was concave up, the tangent line was below the graph, whether it was increasing or decreasing. Well, that's reversed when we have a concave down function. So here's a concave down function, and the tangent line is above the graph. And so here we see as we go to the right one, what's happening is the function is dropping down more than the tangent line. So the absolute value of delta y is bigger than the absolute value of the slope. But we want to put these in order in terms of the actual numbers, since they're both negative. Remember how we order negatives. So a larger drop is a bigger absolute value negative number. So that makes the change in the function, delta y, or delta f, to be actually less than the derivative. More drop, which is less number when you're talking about negatives. Okay? On the other hand, one more case to look at. If we have a decreasing or an increasing but concave down function like the one we have here, again, concave down function means the graph of the tangent line is going to be above the graph of the function. In this case, delta y is actually, and the delta f are both positive, but notice that we're going up more to get to the tangent line than we do to get to the function. So delta y is less than f prime. Okay? So, what's kind of the conclusion? Well, let's see. If f is concave down, we can say that the tangent line is above the graph of the curve. If the f is concave up, we say the tangent line is below the graph of the curve. Of course, it's equal to they're the same point at the point of tangency, at that single point, but nearby. Then we get the tangent line to be a little bit off of the curve. If f is decreasing, let's see, what do we have here? If f is concave up, it turned out that the change in y was actually greater than the change in the function. Okay, that was true here and here. So change in y greater than the change in the function. Here, the absolute value of the change in y was less, but in terms, since they're both negative, the change in y is still greater than the change in the function. So concave up, change in function greater than change in the derivative, than the amount of the derivative. Here, if f is concave down, we found that the change in y was less than the derivative. Be a little bit careful on the negative side, though, to think about what that means. So a smaller number here for the change actually means a larger actual amount of change when you're thinking in terms of absolute change, absolute value change. Okay. Now, so and again, the thing is that these are not the same. Okay, unless the graph is linear, unless f of x here is a linear function, then the delta f and f prime are not the same. However, what we really want to emphasize is not how they're different, but how they're close to the same. And so what we want to do is we want to use one of these to approximate the other. So oftentimes we'll say the derivative is approximately the same as the amount of change in the function. So when we add 1 to x. So that's a good approximation, and we use this word marginal for this in this relationship, we use this in business quite a bit. So the word marginal, we're going to mean in this class is the derivative, but we're going to interpret it to be approximately the amount that the function goes up or down, up if the derivative is positive, down if the derivative is negative, when you increase x by 1. And so then we looked at some examples, application problems, where we put these concepts into work. So I'll refer you back to the other video for that part.